lipid. Did you say that?
Butter.
Oh, piece of butter. I love it. I'm like, well, okay, butter, blubber, butter. I heard blubber. Okay, but they're both lipids, all right? So some form of fat, some form of triglycerides. Some of you might have heard of triglycerides. Here's the cool thing with lipids. All of you, especially biology majors, have seen this cartoon before. How many of you recognize that cartoon? Please, everyone raise their hand. That is the lipid bilayer, right? It is the cell wall. Okay? We are in a chapter by the end that's going to describe why it is that lipids do this. Lipids are these literally triglyceride moieties that have a real polar region and two nonpolar, really greasy tails. And what's really cool about lipids, if you just throw lipids in randomly into water, they will actually spontaneously form this because they're trying to hide, their grease likes grease, polar likes polar. So they naturally arrange themselves this way. But they're not stable, okay? They float. It's literally like the waves on the ocean. They're very, very fluid. So somehow we have to strengthen that. And that's what we're going to talk about when we get into the various different types of lipids and then finally the steroid family, all right? Because it is cholesterol that is a lipid that actually solidifies and makes this more rigid, okay? And that's where we're headed. That's the big picture, the big flyover of lipids. So we're going to talk about a polar region and a really greasy region, all right? So the two main functional groups with lipids are carboxylic acids and esters. Hey, we just had a chapter in carboxylic acids and esters, so it's nice that it flows into the lipid chapter. It makes sense. Here is my carboxylic acid, and here is my ester. Okay? So with lipids, lipids are going to be in one of these forms. Typically, this is the form right here that is the polar region. Carboxylic acids love water because they love to hydrogen bond. That's why we draw the little bilayer with this polar region, and it's going to be this R group that becomes this big, giant, greasy trail, okay? So this is a class, as you're going to see, we're moving into bigger molecules. We're moving into bigger molecules because we're moving into biochemistry. So we'll spend this chapter on lipids. The molecules are going to get a little bit bigger, so the drawing is going to be a little bit more complex. We're going to move from that into amino acids and proteins and enzymes, that's where we get into different types of uptake and inhibition that we talked about. Then we're going to move into 2 chapters of basically PowerPoints. So the last 2 chapters are PowerPoint because they're just the structures are so large, it's really hard to really do talk and do it well. All right, and I know I'm not a PowerPoint. I am not a PowerPoint person. I'm just PowerPoint killed story. We used to learn for over 4,000 years. We learned through story. Story invokes emotion. Story invites you into a journey somewhere. PowerPoint kills that. It's like watching a slideshow of your kids in the Grand Canyon. Big deal. Right? It's really cool for me, but you could probably care less, right? Or couldn't care less, however that phrase works. Okay? So I'm not a fan of PowerPoint. I love story. That's even I get to preach this Sunday at our church Eagle Nav, and one of the things I do in my sermons is I integrate story. I want to invite you into a story because again that invokes emotion. Think of when you went on family vacay, right? What are the ones you remember the most? When your dad locked the keys in the car, when you got in a wreck, when you had a flat tire, when you saw the sunset. when you saw, right? It's the highs and the lows. Oftentimes we don't remember the middle things. It's the beautiful ocean, or it's the, I got to call AAA to get my keys out of the car, right? Or the truck broke down. I was listening to Adam when you were sharing your story. I vividly, when you flip your truck, or it's like that's part of his story. That there's emotion to that, right? That's how we teach. That's how we inspire. We don't inspire through PowerPoint. Golly, what a joke. Okay, so what's going to happen with the with the lipids? Lipids are going to have a big greasy chain. Okay, so this is really what we call hydrophobic. And this is hydrophilic, which was the name of my Malibu ski boat, which I still wish I had. So that's called hydrophilic. So this part loves water. This part hates water. Okay, so this is why we have this polarity, non-polarity thing going on. Since the body is over 80% water, I think that's the stat, something around there, we're mostly aqueous. But we have to have a level of non-aqueous, otherwise when we jump in the water, we'll just dissolve. All right, so there is a component of us that is water insoluble, and that's kind of important. All right, so how do we find the balance of that? Well, we find the balance of that by putting grease or hydrophobic sections in certain areas of the body or within the cells. Okay, so what we're going to see here is that the cell membrane is made from, again, this hydrophobic and hydrophilic interaction. Depending on what this is and what this is, really changes what type of cell I'm talking about. So heart cells have a different lipid bilayer than a liver cell or than the small intestine, which has to have things absorbed through it, right? That's one of those things I think that's really important with understanding that, yeah, hydrophobic and hydrophilic have to work together. Even though they don't like each other, they do work in concert. So this is our first one. This is lauric acid. Lauric acid. Most lipids are going to be ic acid because, again, they're carboxylic acids. All right. So this is a carboxylic acid. Lauric acid is 16 and 1, or 16 and 0. Think of it that way. Now, what that means, the 16 and 0 means it has 16 carbons. Sorry, it has 12 carbons. I'm thinking ahead of myself here. That's 12. Lauric has 12. 12 carbons. And so when you look at this, you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? The 0 stands for the fact that it's saturated. Remember when we dealt with alkenes, we call that unsaturation. So we're going to have a series of these that are actually unsaturated. Lauric is saturated. It's completely saturated, so it has 0 double bonds. That's what that stands for. Right? This is number of carbons. This is the number of double bonds. Okay? Good? Okay, so the next one, again, and by the way, just kind of an easy thing, they're all even. Kind of nice. So they're all even numbered. All right, so our next one, and this, by the way, you find this in coconut if you want that. In fact, if you go, this is coconut oil. If you go to the movie theater, and back in the day, they've actually changed their formula. But back in the day, when the popcorn was really good, I mean like good, where you could do that on your own and put as much butter on as you wanted, that has that in it. And it's what coagulates on the roof of your mouth when you're eating it. And you kind of scrape it off the roof of your mouth. It's really good popcorn. That comes from that right there. That's the good stuff. Okay. So the next one is myristic acid. Myristic acid. Again, ic acid. It's 14 and 1, or excuse me, 14 and 0. Again, it's saturated. Okay, meristic. Next one. 2, 4, 6, 8, 10, 12, 14, 16. Is palmitic acid, and it is 16 and 0. Okay. This one, palmitic, is found in palm. That's just kind of where it's found, but again, it's an oil. Probably the one that most people are familiar with is this one here. I've always thought of this one as one of the better ones because it has a really good flavor. So this is stearic, and I always think of stearic as steer, which means it is in animal fat. So stearic acid is what makes a really good steak a really good steak. Okay, it's also, if you cook hamburger, and at the end, and if it's a cheaper hamburger, you're gonna have all that liquid, that oil that gets hard when it cools down at room temperature. That's stearic acid, okay? So stearic acid is 18 and 0. Am I wrong? Did I count something wrong? What?
I'm not sure.
What did I mark? 2, 4, 6, 8, 10, 12, 14, 16. Am I right on these? 2, 4, 6, 8, 10. Okay, I'm sorry. Yeah, thank you. If I'm wrong, just.
I wasn't positive.
You're like, it is hard, right? You're like 1, 2, 3, 4, 5, 6. Exactly. Okay. So these are all what we call saturated. Okay, saturated fatty acids. All right, so they're fatty hydrophobic acids, carboxylic acid. Okay? And you could probably see where this is going to build. Because, like I said, lipids deal with carboxylic acids and esters. So I'm probably going to connect these here at the carboxylic acid and form an ester. And that's where you get into your triglycerides and your lipid bilayers. All right? So we'll build on this. All right. So we're at 18 and 0. So the next one is 16 and 1. So 16 and 1. 16 and 0 is what? 16-0 is palmitic. Okay? So 16 and 1 looks like this. 4, 6, 8, 10, 12, 14. Okay, so this is 16 and 1. This is palmitoleic acid. Okay? Palmitoleic acid. (18:1) is oleic acid. So again, it looks like this, it just has 2 more carbons. Now, I'm going to stop here and describe something. So, 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. Okay, so this is really an important thing with lipids. We talk about lipids as being saturated or unsaturated, and when they're unsaturated, okay, so this is going to be your unsaturated family. All right, so unsaturated, but what's really important is these alkenes are all cis. or Z, Einwagen and Süßwagen. Okay, they're cis double bonds. That's really important, and here's why. This palmitic acid is a solid at room temperature. Why? Well, what happens with the saturated fatty acids is this big grease thing here, salami or whatever, looks like this. And they stack in on each other. And so one of the interactions that happens, and then they have the CO, you have the OH here. So one of the things that happens with these big is there's an attraction. And we call this London dispersion forces, but there's an attraction, okay? So grease likes grease. So there's an attraction here that I have to actually break up. And it takes energy to break it up. So that's why when they stack, they form a solid at room temperature, all right? Over here, when we get into our olive oil family, here and here, olive oil is a liquid at room temperature. Why? It's because you don't have salami stacking. You have boomerangs. And boomerangs form these weird structures that are not uniform, okay? And it breaks up that attraction. So when we have saturated, all of those attractive forces are nice and ordered together. When I bring in a cis double bond, it breaks it up. And you can see this is where the double bond is right here. Okay, and it's how they actually break up. Now, what I could do with something like oleic acid, I can take oleic acid and I can hit it with hydrogen and nickel, which is a reaction that we have seen. We saw it when we were dealing with the hydrogenation of alkenes. So I could take some beautiful liquid like this one here, one of the components of olive oil. I can hit it with hydrogen and nickel right here. That's going to remove the alkene, and so it's going to go to this. It's going to go to that. What is that? That's saturated. That is stearic acid. So I went from a really nice oil to a solid. So I went from a liquid by hydrogenation to a solid. Okay? And this is exactly how margarine's made. Margarine is a gelatinous sludge that's made in these massive stainless steel vats. They take perfectly beautiful corn oil. They hydrogenate it over nickel. It makes this gelatinous goo. They throw in butyric acid, which tastes like butter, and they put in yellow food coloring. And they put it in these little artificial containers and they sell it as margarine. Okay? We should stay as far away from that as possible. Just use butter, use less. If that's an issue, just don't use as much. It's healthy, it's good, it comes from a cow. Okay, so here's the thing that you might have heard before. 2, 4, 6, 8, 9. So one of the byproducts of the sludge hydrogenation is that right there. What is that? Yeah. You went from cis, under hydrogenation, one of the byproducts is trans. Okay? And so the trans doesn't do this, it does that. And it's the trans fats that have been linked to some strains of cancer.
So unsaturated plus hydrolysis equals saturated?
It's just a byproduct. It's a minor byproduct. What it does is it actually breaks the bond and then reforms. Yeah. So it's a minor product, but it's in there, and that's why it was really big a couple decades ago, where it would say 0 grams trans fats. I remember the big deal when McDonald's moved their fats from the oils that had been hydrogenated to more of a healthy oil, and the flavor of the fries changed, but now the public's used to that. Trans fats have been linked to that, so that's why this process is not a good. And again, it's not, most of it goes to the alkane. Most of the cis goes to the alkane. That's why this is by far the dominant product. But there is around 1 to 2%, if the process isn't done correctly, that forms that trans version of that fat. Okay? And so that's where the 0 gram trans fat comes.
So, who was the first person to think, I'm going to take some perfectly good corn oil,
Yeah.
I'm going to mix it with some nickel, and that's probably going to be something I can sell.
I'm going to make $1 gazillion, right? And then we're going to learn that's bad for you.
Yeah.
Oops. Well, think of it. A lot of the stuff that we have in food preparation, preserve, came from the military for storage, right? Shelf storage. Well, okay. If you Google or look up the history of Frito-Lay, that's a prime example. Frito-Lay, they were the competing companies. Frito was in Texas, Lay was East Coast or West Coast, I think he has both. Frito was the very first person to be able to take that corn, was it chip, corn, whatever the little thing is, and actually package it and sell it, right? He was able to get the military to buy that because it's salty, tastes good, and it had a good shelf life. So it was the very first chip to actually make it overseas. Lay said, I want in on this, but realized that Frito was beating him. So he said, hey, what everyone should do, let's join forces. So that's where you Frito-Lay from. So now they're like, what, 90% of all chips come from that company. But again, all food preservative, okay? That's where Wonder Bread came from. What's so wonderful about it? Well, we strip all the wheat germ off that our body actually needs, and so no bug wants to eat it, so it doesn't decompose on the shelf, so it lasts for 3 months, right? American cheese, what's so American about it? Oh, it can go up on the moon and in the spacecraft, right? So you start to see that we've done a lot of modifications to our food. And white flour and white sugar are probably the two that are killing our society for real. For real. That's for real.
So as you were saying with like military food, especially MREs, which are the meals ready to eat that they package, they dehydrate them and add so much preservatives and stuff that you can actually open one from like Vietnam, if not farther back, and they are 100% safe to eat.
I have my son's really into like stuff like that because we're like meat preppers. And so we watched this video where they were opening up 40-year-old MREs, and they pick it out and goes, wow, it looks a little bad, but it's edible.
I ate
Still.
ones from the Gulf War.
Did you really?
Yeah. They were literally labeled like 1990, 1997. I was like,
But the taste breaks down, right? They still taste pretty good? That's awesome. So yeah, so food preparation, that's where a lot of this modification comes from. Okay? So any other questions on that? Okay, so let's get through our acids, and then get through our acids. So our last three. I'll just say our last three. Our last three are probably three of the most important. So, and I'll explain those. And by the way, there are some things on here that if you're attempting to like memorize or notice, it is carbon 9 where the unsaturation comes from. Okay, it's carbon 9 and carbon 9. That does become important.
Always carbon?
Always, except for arachidonic acid. Yes, that's an exception. Okay, so our next one, so you think of the pattern here, right? We did 12, 14, 16, 18. We went back up and we did 16 and 18. Now we're going to do 18, 18, 20, okay? So 18, but this one is 18 and 2, so it's different than oleic acid. So 18 and 2 looks like this. And again, like I said, this is one of the most important ones from a health perspective. Okay, so this, notice, is polyunsaturated. So, and I gotta go 18. 2, 4, 6, 8, 10, 12, 14, 16. So notice, this is monounsaturated. These are monounsaturated. These are polyunsaturated. Okay? Now, this one is massively important in our diet. And here's why. You probably know it is this, and I don't know why biochemists do this, they do it wrong, but that's the way it is. Notice this. This is, actually the name of this is linoleic acid. Okay. Sounds like oleic acid, linoleic acid, one more double bond. But here's how you probably know this. 1, 2, 3, 4, 5, 6. You probably know this as omega-6. Okay? It's one of those that we need to take on a regular basis. We find it in flax, find it in fish oils. Salmon's loaded with omega-6 and omega-3s, but really important for health. And by the way, this is one of the things that's stripped out during the refinement of wheat process. When they refine wheat to make white flour, they actually take the wheat germ off of it, which is the part that decomposes because it has the oil in it, and it becomes rancid. It's also what bugs eat. So when they remove that, you're stripping away the stuff that our body actually needs for health.
So is omega-3 fish oil too?
Yeah.
So what's the difference?
I'll show you. This is the next one. Great segue. So the next one is 18 and 3. Yeah. I forget which one comes from. One comes from plants. One comes from animals. That's the basic difference. But they both contribute the same in the body. So this is. This is linolenic acid, and it is 18 and 3. And if you look at this, again, 18 and 3, but notice how 18 and 3 all cis bonds, but notice it is omega, 2, 4, 6, 8, 10, 12, 14, 16, 18, 1, 2, 800. So it is 1, 2, 3. So this is your omega 3. Okay? I think omega 3 is animal based and omega 6 is plant based, I think. But is that the way it is? Okay. Okay. Yeah.
Are they supposed to have the same spelling?
Linolenic, linoleic. There's an N in here.
Oh.
Linolen,
Am I-
linoleic. I know they're like what is it? Twins. Linoleic, linoleic. Okay. And our last one, and probably again one of our most important, is good old arachidonic acid. So arachidonic acid sounds like arachnids, but it's not. The reason why arachidonic acid is so important is one that actually contributes quite a bit in our health. So it is 2, 4, 6, 8, 10, 12, 14, 16, 17, 18, 19, 20. Okay. So this is arachidonic acid, arachidonic acid.
What was that?
Arachidonic acid. Arachidonic acid. Arachidonic acid. This is a really important one. The last three, from a health perspective, omega-6, omega-3, arachidonic acid, is really important. And this is 20 and 4. If you like to keep score like that, arachidonic acid is 20 and 4. But here's why arachidonic acid is so important. Arachidonic acid does this really cool, almost like, remember back in the day when we tipped our carbohydrates and we did kind of a funny thing? This is why arachidonic acid is a really important. 1, 2, 3, 4, 5. Okay. So arachidonic acid actually coils in on itself. And here's why this is so powerful. It actually forms a bond between this carbon and this carbon. And when it does that, it forms these massively powerful and important molecules that look like this. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, 1, 2, 3. Okay, so here, stay with me on this. There is a whole family of these. All right, I think your book has 3 or 4 in it. It shows these are prostaglandins. Okay? Our body naturally takes arachidonic acid, which we have to have through diet, forms prostaglandins. This is what inflammation and pain comes from. So if you're taking one of the NSAIDs like acetylsalicylic acid, ibuprofen, naproxen, fluorobiprofen, ketoprofen, any of the fen family, you're actually blocking the formation of the prostaglandin. That's how the NSAIDs work. They inhibit this step so that we don't have pain, okay, or inflammation. Okay? So arachidonic acid becomes the prostaglandin family. Now, like I said, there's several. There's some that have a trans bond here. Most of them have the hydroxylate 6, 1, 2, 3, 4, 5, 6. Some of them put a double bond here that's trans. Some put a double bond here that's cis. Okay? But they all kind of have that general structure. And they're very important because what happens is this hydrogen here is what bonds to the protein that is undergoing this whole transformation in the pain model. Okay? I'll pick this back up. We'll look at this a little bit deeper when we get back from spring break. And have a great break, have a safe break. And yeah, I'm just excited that we'll come back and finish the journey, finish the story. No, they just want to show you where it actually all is done through an enzyme. Yeah, so the chemistry is actually an enzyme, but that's the carbon. No, we're not going to do it. We did.
I know we were there.
That wasn't the
Well, my uncle was huge.
That was the plan originally. Yeah, well,
There's so much fun.
I'm not.
We went 2 years ago and we were like, oh, this is fun. And my niece, like, it was her birthday, so like, oh, yeah, let's go again. And I'm like, no, I'm too much. So we had to wait like another time. It's like, then we can go again.
That's so
I know, fun is fun. Except the traffic there is awful.
Is that right?
It's a 2-person. Yeah.
Wow.
My mom's a scary driver. I'm like, mom, please don't.
I love it. That's so cool.
I just want to let you know, my Monday just looks like a flight. My schedule is right out.
So what is
I don't
being an RA for like
attendance, so.
that in jail?
Okay, yeah, just get the notes because we're going to pick it up with this stuff here too. Okay. Cool.
Where do you want to stay?
Cheers. Cheers. Put it in your library. Get your book.